Thank you very much. Good afternoon, everybody. My name is Patricio Vos. I work at the Naval Research Office and the National Council of Scientific Research in Argentina. I'm here to present this portable experimental buoy for coastal acoustic monitoring with application to the Argentinian continental shelf. So why is it that we are interested in monitoring acoustically the continental shelf? First, let me give you some background to put this work into context. We know airgun arrays using seismic surveys generate high amplitude pulses that, with given condition, can propagate ocean basin scales for thousands of kilometers and reach IMS hydroacoustic stations with high signal-to-noise ratio. Furthermore, these signals can be used to validate long-range propagation models. However, limitations exist on the high directionality of these sources and the shallow water propagation environment that reduces detectability. And there is also the challenge of synchronizing ground truth of the airgun shots with the actual station recordings. Recently in Argentina, seismic surveys have conducted for the offshore oil and gas industry and have produced large data set of high amplitude signals. We modeled these signals with the Agora software and found the energy concentrated in the 5 to 70 hertz band. For properly study these signals, we need local measurements and to identify proper selection for semi-permanent hydrophones deployed from a buoy. So we studied the acoustic coverage from the Ascension Island station, H2, by running simulation with the range-dependent acoustic model. The acoustic scenario includes realistic oceanographic data from Copernicus and bathymetry from Ch2. Although we compute transmission losses in the 2 to 100 hertz band, for the purpose of this presentation, we'll show results on only 4 frequencies. And we are considering a depth of the source of 8 meters. We want to perform a maximum coverage analysis considering high amplitude source levels and a threshold for transmission losses of 200 dBs as an exploratory threshold. The results here are shown for a frequency of 10 hertz. We appreciate a strong frequency dependence on the transmission losses. There are large coastal shadow zones, and with increase of the frequency, the coverage improves but remains limited for shallow waters. The Argentinian continental shelf begins in the isobat of 200 meters, the black line in the map. And we found that it acts as an acoustic filter with acoustic coverage gaps where long-range IMS stations miss near-shore regions. There is a local minima for transmission losses in the continental slope. In particular, well, these are higher frequencies. In particular, this is the site where the Ara San Juan wreckage happened. The signal from the 2017 implosions were detected by 2 IMS stations, and we analyzed these signals in our previous work. So with all this information, we selected 2 candidate sites for buoy deployment. One in the north part of the shelf, offshore the city of Mar del Plata in red, and another one in the south, offshore the city of Comodoro Rivadavia in green in the map. Now we want to assess the acoustic coverage of each site independently. For the first site, we use the same acoustic scenario. Here, the receiver depth is different because we are in a shallow water environment, and we run our 2-dimensional model on all these radial transects. The results again show strong frequency dependence. At low frequencies, there are large shallow zones. We found a filtering effect on the continental slope that reduced transmission for low frequencies. The coverage is improved for mid-frequency, the 50 hertz and 80 hertz. But shallow water gaps remain. There are limited detectability close to the coast. And we found that buoy deploying hydrophones in this part of the shelf would improve the coverage in the northern part of the shelf. We did the same analysis for the second candidate site near Comodoro Rivadavia in the south. Results show a marked frequency variation with stronger propagation losses at 10 and 20 hertz rather than 50 and 80 hertz. The coverage extends further to the shelf and beyond the slope. Hydrophones deployed on this station would improve the coverage in the southern part of the shelf. And we found that each site complement each other, covering different parts of the shelf. So to perform these measurements, we designed a buoy platform designed for hydrophone deployment. The main objective is to characterize ambient noise and other underwater sources on the continental shelf, and to contribute to the understanding of shallow water propagation effects. It has the potential, combined with IMS hydroacoustic stations, to contribute to the understanding of shallow water acoustic propagation. This custom designed buoy is a prototype specifically designed for the deployment of hydrophone arrays in the near shore on semi-permanent stations. It features a glass reinforced hull, 3 mooring line for a stable position. It works on a standalone basis operated by solar panels. It has a sealed electronic compartment and a central mast for sensors and antennas. And it's designed to withstand harsh marine conditions, strong currents, and waves up to 4 meters. The electronics are mounted on a lift-out aluminum rack that houses an embedded computer, an audio interface, low-noise hydrophone preamplifiers, an automatic identification system for navigation safety. It has a satellite model and a deep cycle battery. The software running on this embedded computer is organized on a layered architecture. On top level, we have an orchestrator who is responsible for coordinating the overall system flow. It decides which part of the system to activate and when. It handles the high-level internal and external events. On the middle layer, we have state machines that manage module behavior based on the current state of the system and react to events and execute actions and changes the internal states. On the lower level, we have the driver that directly interacts with the hardware, performing input-output operations and peripheral configurations. For each module, the logic is managed by a finite state machine. We use the same pattern on all the modules. The normal path of execution would be to start disable with all the resources released. Then the orchestrator would send an init signal where the hardware is initialized and internal variables are set. Then comes a self-test that verifies the correct functionality of the module. In case of an error, recovery attempts are performed. If succeed, system goes back to normality. If not, it's safely shut down. And on the other hand, if the test goes okay, the module goes to the idle state awaiting for commands. And finally, when activated, the module executes its specific tasks. To conclude, a new platform for underwater noise measurements was developed for shallow waters of the Argentinian continental shelf with application to impulsive sound monitoring. It has the potential for basing scales propagation analysis using impulsive signals that can be detected by the IMS hydroacoustic stations. It is a low-cost prototype buoy for coastal acoustic monitoring that it is in its final stage of integration. The 2 proposed sites, deployment sites, were selected to enhance monitoring in uncovered regions. And we think these platforms could pave the way for a scalable coastal monitoring system supporting both scientific baseline studies of shallow water soundscapes and long-range propagation analysis. As a further work, we are actually working on improvement for the coverage analysis, running 3D models based on the split-step Fourier method. Details on this work can be seen in this mentioned poster. And as a sneak peek, I leave you with this run of the 3D model from H10 to our continental shelf. And I thank you very much for your kind attention.
Thank you, Patricio. Any question for Patricio, Mario?
Yes, thank you. Very, very interesting system. My question is this system transmitting detection, so it's doing onboard processing, or are you also transmitting data in real time to shore?
Both things. The embedded system has the capability of listening and processing the information, and the satellite model would transmit a process chunk of the information.
Okay, but process, not raw data.
No,
okay.
no raw data. No.
Thank you very much. Thanks, very nice.
Any other question? So when is the system planned to start working? And
that's a good question. The technical part, the technical integration part would finish first month of next year. Hopefully, we'll have this system installed and operating by next year, sometime next year.
Okay, thank you.
Thank you very much.